radiologists' imaging is based on the physics principle of nuclear magnetic resonance, or NMR, first described in the 1930s and 40s. The basic principle of NMR deals with the interaction of certain atomic nuclei, radio frequency energy, and a strong magnetic field. MR images are made up of a series of voxels, or volume elements. Each square on the picture corresponds to a volume of tissue on the body. The MR machine is designed to measure the NMR signal from each of these small volumes, localize them in 3D space, and plot them on a 256 by 256 or 512 by 512 matrix to make a visible picture. The rate of precession can be determined exactly by the Larimore frequency equation, which states that the rate of rotation is directly proportional to the strength of the local magnetic field. At 1 Tesla, the Larimore frequency of a hydrogen proton or spin is 42.58 MHz. At 2 Tesla, 85.16 MHz, and at 3 Tesla, 127.74 MHz, or basically 42.58 MHz per Tesla. This will be important when we're talking about making an image from NMR data later on. The first to propose the use of NMR to diagnose disease in humans was Dr. Raymond Damadian, who in the March 1971 edition of the journal Science published a short article entitled Tumor Detection by Nuclear Magnetic Resonance, in which he suggested that the NMR signal from tumors in the body could be differentiated from normal tissues and therefore could be detected. His original concept was not to make an anatomic picture, but to build a detector large enough to accommodate a human, perform a whole body NMR, and look for a characteristic T1 and T2 tumor signal that would suggest you have a malignancy somewhere in your body, sort of a quick screening tool for malignancy. While Dr. Damadian's tumor detector never came to fruition, we do use MR spectroscopy in conjunction with a standard MR image to help distinguish benign from malignant processes in the body. To make an NMR picture, or MRI as we know it today, we have to be able to localize the signals coming from the sample or tissues in 3D space. The first to propose a technique to do just that was Dr. Paul Latimer. In the March 19, 1973 edition of Nature, Latimer published a brief article entitled Image Formation by Induced Local Interactions, Examples Employing Nuclear Magnetic Resonance. In the article, he describes a technique using magnetic gradients to identify the location of two 1 mm capillary tubes filled with water, both of which were submerged in a larger 4.2 mm tube filled with heavy water. Latimer placed his apparatus in the high-field NMR magnet as shown and developed a technique to identify the actual origin of the NMR signals from the standard water. This is the image produced. Very primitive by today's standards, but clearly shows the location of the two capillary tubes of standard water. Latimer called his technique zeugmatography from the Greek zeugma, which means that which is used for joining. When we first get into the MRI machine, a superconducting magnet creates a near homogeneous magnetic field from one side to the other that determines the strength of the MRI machine. Common systems are 1, 1.5, and 3 Tesla in strength. There are 3 sets of gradient magnets in the MRI used to localize locations in 3D space. The Z-axis, X-axis, and Y-axis. To select a particular slice of tissue in the body, we can turn on the set of electromagnets along the Z-axis that create a magnetic gradient from head to toe. We now put in a radio pulse with a frequency that will cause the desired area to resonate as described earlier. We have now selected our slice through the body. Each of these squares or voxels are assigned a grayscale value corresponding to the strength of the local signal, by convention, white being a strong signal and black being no signal at all. In this simplified example, our 4x4 matrix doesn't look like much, but a standard MRI with a 256 by 256 or 512 by 512 matrix will provide exquisite anatomic details of the body.